Okay, so this problem here is a energy level diagram problem. The given information, it's in one sentence. The allowed energies of a simple hypothetical atom are -6 electron volt, -3 electron volt, -1 electron volt. Hey, electron volt, electron volt is a unit of energy. No joking around. It's a serious matter, man. Serious. Volts. Electron volt is a unit of energy. What else is a unit of energy? Joules. So I'm just going to put up here as a side note, in parentheses, just 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules. Very easy number to remember because this is the charge of an electron, right? So easy to remember. Now, they want us to, first of all, draw the atom's energy level diagram. So these are the energies of the levels. So it goes like this. So question A, you're doing, the idea here is that, you got the nucleus in the center, and then you have these energy levels that go around the nucleus like this. And what they've given you is the energy of each level. Okay, but the way you draw it, you're not going to do it like this. You're going to show just parallel lines like this. So you go, okay. Boom. Let's see, we got -6, -3, and -1. So we'll put this at the bottom. So the nucleus would be down here. This is the n equals 1. That's the smallest energy. -6 is the smallest on the list, guys. -6 is the smallest. So the -3 would be up higher like this. That's -3. That's bigger. And then -1. And that's n equals 1. This is the n equals 2, n equals 3, right? When they say the principal quantum number, that's the number of the energy level. So this is the answer to A. So this is the first energy level, second energy level, third energy level, and then these are their corresponding energies. The smallest energy goes closest to the nucleus. As you go away from the nucleus, the energy gets bigger. Just like on, just like with gravity. If I take this apple, if I move this apple away from the earth, what happens to its energy? It increases. Okay? All right, so that's A. B, calculate the wavelengths associated with each possible transition between energy levels for the atom. All right, so now what are the possible energies? First of all, they're asking for, they're asking for wavelengths, but before you figure out wavelengths, you got to figure out what the energies are. So look, if you had an electron in this energy level up here, if that electron fell all the way down, how much energy would be released by the atom? 5 electron volts, right? The idea here is when electrons fall towards the nucleus, energy is released. If an electron moves away from the nucleus, energy is absorbed by the atom. Okay, now what else could this electron have done? This electron could have done that and then taken a little break. So how much energy would that transition be? 2, and then it could have fallen the rest of the way. 3 and 6 would be 3. It's just the difference between these energies here. Okay, so there's 3 possible energies. Now, oh, and by the way, that energy is being released in the form of what? Light. This energy, like this 2 right here, is coming out. It's a little photon leaving the atom, right? So how do we find the wavelength associated with that photon? Well, there's 2 equations. The energy of a photon is equal to Planck's constant times frequency, and Planck's constant's given. And then we also need the wave equation. Velocity is wavelength times frequency. But since we're talking about light here, we're talking about light, right? So what can we replace this V with? C. We can replace that with C. Now, if you substitute these 2 equations together, if you go like this, frequency, so take this equation here. Frequency is going to be C over lambda. Plug that in up there. You get E equals hc over wavelength. So wavelength is hc over E, right? If you look at the table of constants, you'll have this on the exam. hc is given, or you could calculate it out, right? But hc is on here. It's 1,240 nanometer times electron volt. Is that correct? Hold on. Yes. Okay. And then divide by E. So look, how do we get the wavelength of this guy? Divide this by, what's the energy of that guy? 2. Okay, so you divide that by 2. This is 620 nanometers. So this guy right here has a wavelength of 620. Okay, how do we get the wavelength of this guy? Just change the 2 to a 3. And then that comes out as, what's that one going to be? 413 nanometers. So this guy is wavelength 413. And then how do we get the wavelength of this guy? Just change that to a 5. And then that gives us 248. So those are the 3 possible wavelengths, right? Ooh, I like that game. That's going to be my summer addiction, that game. Okay, moving on. Okay, part C. Okay, part C. The atom is in the ground state. Okay, shoot, I lost my diagram here. Boom, put it back. So here's the diagram. So we got -6, -3, -1, and then there's n equals 1, n equals 2, n equals 3. Okay. The atom is in the ground state, which is this one down here. Okay, ground state is the n equals 1. Okay, so the electron is in the n equals 1. When an electron traveling with a speed of this collides with it, can the electron excite to the n equals 2? So look, how much energy would be required to boost this electron up to the n equals 2? How much energy would we need to do that? Well, 6 and 3. How much energy would be needed? We would need what? 3 electron volts. So let's see if we have it. How do we figure out? So they're talking about this. They're talking about this incoming electron, right? Coming in, bam. We need to find the energy of this incoming electron. Can we do it? Yeah, man. What type of energy does this electron have? Kinetic. So the kinetic energy of the incoming electron, kinetic is 1/2 mv squared. So that's 1/2 mass of electron. Don't panic. It's given. It's on your test. The mass of an electron, 9.11 times 10 to the negative 31, and then times velocity squared, 1.3 times 10 to the 6, times 10 to the 6 meter per second. Make sure you square that. So this gives us a kinetic energy equal to 7.698 times 10 to the negative 19 joules. But then what do we have to do to that? We need to convert it to what? Electron volts, right? So look, joule and electron volt. What's the conversion? 1 electron volt is 1.6 times 10 to the negative 19 joules. So this whole thing comes out as 4.8 electron volts. Is that correct? Yeah. This comes out as 4.8. So dudes, is it possible for this incoming electron to boost this guy to the n equals 2? Yeah. Because how much energy is needed? 3. How much energy is coming in? 4.8. That's enough energy. The answer is hell to the yeah. Yeah. And you said that. Just change this right here. Just say, hell yeah, brother. I don't. Okay. No, don't do that. I'm kidding. I'm kidding. Don't do that. Just say yes, sir. Yes, sir. Okay. And then justify your answer. A. Justify your answer. 3 electron volts needed. 4.8 electron volts provided. Something like that. Okay. Part D. We're almost done here. Another electron excites the atom from the ground state. So, dude, I'm going to redo this whole thing real quickly. So here's -6, -3, -1. This is the n equals 1, n equals 2, n equals 3. Okay, another electron excites the atom from the ground state to the n equals 2. So this guy goes from the ground state up to here, right? Let's see what happens. The atom then decays back to the ground state by emitting a photon. Okay, how much energy is going to be released in that process when it falls back down from the n equals 2? 3 electron volts. Okay, calculate the energy of the emitted photon in joules. Ooh, we have it in electron volts. Okay, 3 electron volts, convert that to joules. 1 electron volt is 1.6 times 10 to the negative 19 joules. Cancels. That's 4.8 times 10 to the negative 19 joules. Easy. Okay, now, in what region of the electromagnetic spectrum is the radiation? Okay, I got to explain this a little bit. So, dudes, you should know. So here's the electromagnetic spectrum. So let's go from low energy to high energy. So over here is going to be low energy. Over here is going to be high energy. What has low energy on the electromagnetic spectrum? Radio waves. What else does? Microwaves, right? And then we get infrared. Infrared's not going to hurt you. All this stuff won't hurt you. I guess microwaves could hurt you, but they're low energy. Okay, then after infrared, we get visible. There's visible light. Then after visible is UV. Then we get X-rays. Then we get gamma rays. So just be familiar with the electromagnetic spectrum. One thing to know, dudes, if I was you, I'd kind of just memorize this. Visible light has a range of 400 nanometers to 700 nanometers. The range of visible light is 400 to 700. So which side would be the 400 and which side is going to be the 700? Long wavelength, let's see, is long wavelength high energy or low energy? Low. You can figure it out from the equations, right? E equals hc over wavelength. I just showed you that. If your wavelength is big, then your energy is low. So 700 nanometers would be over here, and then 400 nanometers is over there. So anyway, what we got to do, they want us to figure out in what region of the electromagnetic spectrum is this radiation. So what do we have to find out about this 3 electron volts? We got to find its what? Wavelength, which we actually already did, right? That was what? This was 413 nanometers. We did that earlier. So where is the 413 nanometers going to be? In the visible. It's going to be in the visible section. Done.